In the realm of space situational awareness, stripe-like space target detection, SSTD, is crucial for understanding spacecraft behavior. However, this domain faces three primary challenges: the lack of publicly available datasets, interference from stray light and stars, and the variability of stripe-like targets, which complicates pixel-level annotation. To address these challenges, the authors introduce AstroStripeSet, a pioneering dataset designed for SSTD. This dataset is specifically tailored to tackle the aforementioned challenges, providing a robust foundation for future research. The authors also propose a novel pseudo-label evolution teacher-student framework with single-point supervision. This framework leverages the zero-shot capabilities of the segment anything model, SAM, in a single-point setting to generate initial pseudo-labels. Subsequently, the fine-tuned StripeSAM serves as the teacher, and the newly developed StripeNet as the student, iteratively refining the labels and consistently improving segmentation performance. A key innovation of this framework is the introduction of GeoDice, a customized loss function designed to accommodate the linear characteristics of stripe-like targets. This loss function enables the model to effectively learn from the pseudo-labels and adapt to the complexities of SSTD. Extensive experiments demonstrate that the proposed approach matches fully supervised methods on all evaluation metrics, establishing a new state-of-the-art, SOTA, benchmark. The authors plan to make their dataset and code publicly available, facilitating further research and development in the field of SSTD. The significance of this work lies in its ability to tackle the challenges of SSTD using single-point supervision, paving the way for more efficient and effective space target detection. The introduction of AstroStripeSet and the pseudo-label evolution framework provides a robust foundation for future research, enabling the development of more accurate and reliable SSTD systems. The detection of stripe-like space targets is a critical and challenging task in space surveillance and research. High-precision and high-resolution optical telescopes capture these targets as stripes or Gaussian points within their field of view, depending on the operational mode and exposure duration. However, extended exposure times increase vulnerability to space stray light interference, which compromises the signal-to-noise ratio, SNR, of stripe-like targets. Despite the maturity of research on point-like space target detection, the exploration of stripe-like target detection remains in its infancy due to several challenges. A unified, open-source, and large-scale dataset for thoroughly benchmarking detection algorithms is lacking, primarily due to the difficulty and high cost of acquiring real space images. The low SNR caused by space stray light interference and numerous stars further complicate the label annotation process for data-driven methods. The variability in the appearance of stripe-like targets, including differences in position, scale, direction, and brightness distribution, poses a challenge to traditional detection methods. This necessitates more adaptable and robust approaches. The challenges in stripe-like space target detection, SSTD, include space images with varying stray light, as shown in Figure 1. The investigation into SSTD holds significant promise for enhancing space surveillance and research capabilities. The scarcity of public datasets for deep learning research in stripe-like space target detection has been addressed by the introduction of the AstroStripeSet dataset, the first of its kind. This dataset comprises synthesized images under various stray light scenarios with annotations in multiple formats, filling a critical gap in the domain of space target detection under stray light conditions. Foundation models, such as Dino and SAM, have demonstrated remarkable zero-shot capabilities in computer vision. However, adapting these models to specialized domains like space images requires fine-tuning strategies to effectively leverage their capabilities. To address the challenges associated with obtaining ground truth images for fully supervised learning methods, the authors explore the feasibility of single-point weak supervision for space target detection tasks. A novel teacher-student framework for pseudo-label evolution is proposed, which utilizes the zero-shot capabilities of SAM to generate initial pseudo-labels from point annotations. The teacher model is fine-tuned through low-rank adaptation with the filtered pseudo-labels and can segment more weak texture stripes. The refined pseudo-labels are employed to train the student model, StripeNet, to distill knowledge from the teacher model and enlarge the search space for better pseudo-labels. This iterative teacher-student mechanism facilitates the evolution of pseudo-labels and improves the accuracy of space target detection. A new loss function, GeoDice, is also proposed, informed by the linear-like shape characteristics of stripe-like space targets. Experimental validation demonstrates that the framework achieves state-of-the-art performance, comparable to fully supervised methods across various metrics. The contributions of this work include the introduction of the AstroStripeSet dataset, the development of a novel teacher-student framework for single-point weekly supervised training, the proposal of the GeoDice loss function, and extensive experimental validation. This section provides an overview of existing methodologies for stripe target detection in complex backgrounds, categorizing them into three approaches: geometric feature-based, pattern-based, and data-driven. Geometric feature-based methods leverage parameter spaces or integral transformations to detect stripe targets, often employing the Huff or Radon transforms. However, these methods face limitations in handling background clutter, noise, and variable scales of targets due to the inherent properties of the Huff and Radon transforms. Pattern-based approaches commence with filtering algorithms to mitigate space stray light and stars, followed by the design of multiple stripe matching templates of different orientations to detect stripe-like targets. These methods struggle under strong stray light interference and fail to detect weakly manifested or morphologically distinct stripe-like targets. Data-driven approaches integrate convolutional neural networks, CNN, into stripe target detection, focusing on automatic learning of stripe features from extensively labeled images. These data-driven methods have achieved state-of-the-art performance in stripe target detection, but their reliance on large datasets and computational resources poses limitations. In contrast to these existing methodologies, the proposed approach introduces a novel teacher-student single-point supervision method for stripe target detection, detailed in Section 4. The AstroStripeSet dataset, used for experimental validation, is presented in Section 3. The stripe-like space target detection task has been approached through various methods, including hierarchical network structures based on UNet, which mitigate stray light interference. However, these methods require pixel-level annotation, and their performance under intense stray light remains unreported. Universal target detectors, such as YOLO and RCNN series networks, struggle to achieve optimal results due to the variability of stray light and stripe-like targets. Advanced networks, including ISNet, ACM, DNANet, APGCNet, and RDIAN, also rely on pixel-level annotation, highlighting the need for weakly supervised learning and foundation models to overcome dataset availability and annotation costs. This limitation has led to a scarcity of open-source datasets in SSTD, underscoring the importance of developing comprehensive and diverse datasets. To address this gap, we introduce AstroStripeSet, a pioneering dataset that surpasses existing datasets in terms of volume and background diversity. AstroStripeSet is synthesized to emulate complex space scenes, encompassing a diverse array of space stray lights and sensor disturbances, including reflections, cosmic rays, and stellar background interference. The dataset features stripe-like targets with diverse positions, scales, orientations, and brightness distributions, offering a rich resource for SSTD methodology development and testing. AstroStripeSet provides three distinct forms of annotations: single-point annotation, precise pixel-level annotation, and bounding box annotation, catering to a wide range of research needs. The dataset comprises 1,500 combinations of raw images and their corresponding labeled images, facilitating more robust and comprehensive model training and testing. A comparison with existing datasets in Table 1 highlights AstroStripeSet's unparalleled advantages, including its significantly larger volume and diversity. A novel dataset for stripe-like space target detection has been created, addressing the lack of dedicated resources for exploring stripe detection in space images. This large volume dataset with diverse annotations promotes transparency, reproducibility, and collaborative advancements in the field. The proposed teacher-student framework consists of two core components: StripeSAM, a low-rank adaptation fine-tuned as the teacher network, and StripeNet, the student network. These elements facilitate the progressive refinement of pseudo-labels. A customized GeoDice loss function is introduced for StripeNet, enhancing its ability to discern and segment weakly textured stripe-like space targets. This innovative loss function leverages the inherent straight-line-like prior information of stripe targets, significantly bolstering the segmentation capabilities of both StripeSAM and StripeNet through their collaborative iterative evolution. The initial pseudo-labels are generated using a pre-trained SAM, involving feeding space images into an image encoder for generating image embeddings. Concurrently, annotated target point labels serve as point prompts for the stripe target area, and are input into a prompt encoder for prompt embeddings. The mask encoder generates pseudo-labels by mapping image and prompt embeddings. The proposed dataset offers a dedicated resource for exploring stripe detection in space images, promoting transparency, reproducibility, and collaborative advancements in the field. The dataset's open accessibility and multifaceted annotation approach make it poised to catalyze significant progress in detecting and analyzing stripe-like space targets. The stripe-like space target detection (SSTD) method is a single-point supervision technique for segmentation tasks, applied to the AstroStripeSet dataset where images contain one object each. The process begins with pre-processing images and point prompts using a pre-trained SAM model, which outputs noisy segmentation masks. These masks undergo a connected area check process to remove false positives and detect the number of objects in each image, ensuring that only images with one object are retained. This step results in an initial pseudo-label set, Y0. The pseudo-labels are then used to construct an initial training dataset, D0, consisting of input images, point prompts, and pseudo-labels. This dataset is sent to subsequent modules for further refinement in the loop of label evolution. The page also introduces StripeSAM, a module that utilizes LoRa fine-tuning as the teacher model. Despite its proficiency in zero-shot segmentation under high signal-to-noise ratio (SNR) scenarios, the pre-trained SAM has limited capabilities in segmenting striped images under low SNR conditions. The StripeSAM module aims to improve upon this limitation by leveraging LoRa fine-tuning techniques to enhance segmentation accuracy in challenging scenarios. In this research, a novel approach to enhance the recognition of striped targets in astronomical images under intense stray light conditions is developed. The authors address the challenges posed by inadequate training samples and lack of prior knowledge about stripe patterns amidst stray light. They fine-tune the SAM model with a selected dataset, resulting in StripeSAM, which serves as the teacher network in the label evolution framework. StripeSAM demonstrates superior label quality over the pre-trained SAM and enriches the dataset with additional pairs of weakly labeled data. The authors also introduce StripeNet, a streamlined encoder-decoder architecture designed to leverage the enhanced stripe pattern recognition capabilities of StripeSAM. This student network is trained using the dataset generated from the teacher network, refining the quality of labeling and expanding the repository of data pairs with weak masks. To train StripeSAM, point prompts are required. The mass central point of the detected area in each segmentation map is calculated for point prompts Ps. A new dataset, Ds, is constructed and cycled back to StripeSAM. The label change process is initiated from pre-training SAM with single-point labels and then iteratively loops in the teacher-student framework, referred to as the label evolution. The authors observe that as the label evolution begins, more and more pseudo-labels under conditions of intensive stray light will be exploited. The authors introduce a novel loss function, GeoDice loss, to enhance the segmentation of stripe-like space targets. This function comprises two components: geometric alignment loss, LG, and weighted dice loss, LD. The GeoDice loss is designed to incorporate geometric direction information, yielding segmentation results that more closely resemble real straight-line stripes. To implement this loss, the authors divide the binary prediction map into connected regions, calculate the longest straight line in each region, and compute the angle difference between the straight line and the ground truth and prediction. This angle difference is then multiplied by the sigmoid output of the predicted image to ensure differentiability, and the average of these angle differences is taken as LG. The GeoDice loss is calculated as the weighted sum of LG and LD, with weighting values alpha and lambda. This loss function is used to optimize the segmentation model, which is trained on an in-house dataset consisting of 100 images each, divided into 4 subsets corresponding to different stray light conditions: sunlight, moonlight, earthlight, and interstellar mixed light. The experimental setup is outlined, including the evaluation metrics used to assess the method's performance. These metrics include mean intersection over union, MIOU, and boundary IOU, BIOU, which provide a comprehensive overview of the experimental framework. The dataset and training parameters are also described, ensuring a detailed understanding of the methodology employed. The performance evaluation of the StripeSAM algorithm is presented in Table 2, encompassing metrics such as the dice coefficient, probability of detection, PD, and false alarm rate, FA. These metrics provide a comprehensive assessment of the algorithm's segmentation precision and target detection capabilities. The computational setup and training configuration for StripeSAM and StripeNet are detailed, highlighting differences in training epochs, learning rates, and batch sizes. A comparison with state-of-the-art, SOTA, networks demonstrates the superior performance of StripeSAM under various stray-like conditions. Quantitative results show that StripeSAM outperforms SOTA networks in terms of dice coefficient, PD, and FA, indicating higher accuracy and better target detection. Visual evidence supports the qualitative evaluation, showcasing StripeSAM's effectiveness in detecting stripes under challenging environmental conditions. The proposed method is visually compared to the state-of-the-art fully supervised network on the AstroStripeSet, showcasing superior performance in segmentation accuracy and reduction in manual annotation time. Quantitative results demonstrate the proposed methodology's superiority over various state-of-the-art techniques, including UNet, ACM, DNANet, AGPCNet, RDIAN, MResUNet, and UC-Transnet, as well as pre-trained single-point prompt SAM models. The teacher-student network significantly outperforms pre-trained SAM models across all 4 categories of challenging test images, achieving a performance level comparable to fully supervised network methods. This enhancement is attributed to the innovative implementation of a new label evolution network and the introduction of a customized GeoDice loss function. The comparison also reveals the varied performance of different state-of-the-art methods under each stray light condition, providing a nuanced view of their respective strengths and limitations. The proposed method's superior performance is evident in its ability to accurately segment images while reducing manual annotation time, making it a promising solution for real-world applications. The proposed StripeSAM method demonstrates proficiency in detecting targets within low signal-to-noise ratio environments. A visual comparison with state-of-the-art networks in 8 images of space stripe targets under various stray light conditions, as shown in Figure 3, highlights StripeSAM's performance. Pre-trained SAM loses its ability to segment stripe-like targets under low SNR, while RDIAN produces a high number of false alarms. In contrast, StripeSAM exhibits commendable performance, comparable to fully supervised UC-Transnet, in retaining stripe details throughout the challenging images. StripeSAM consistently identifies true targets, minimizes misses, and avoids false alarms with notable accuracy, substantiating its potential as a superior alternative to fully supervised SOTA methods in stripe-like target detection amidst low SNR. An ablation study investigates the effect of tuning the rank parameter in StripeSAM, crucial for modifying the additionally introduced trainable weight parameters effectively. The results, presented in Table 3, show that a rank setting of 512 yields the most balanced and superior performance across all 4 evaluated datasets. This optimal rank value is adopted within the teacher-student network framework to optimize the balance between efficiency and task-specific adaptation effectiveness. The paper presents a comparative analysis of different loss functions for the first iteration of StripeNet, a model designed to detect stripe-like space targets. The results are shown in Table 4, where traditional segmentation loss functions such as weighted dice loss and soft IOU loss, along with their ensembles, are compared against the customized GeoDice loss function. Each loss function is paired with focal loss in an equal weight ratio of 1:1. The quantitative results demonstrate that the GeoDice loss function effectively leverages straight-line prior information, significantly improving the detection rate of stripe-like space targets while ensuring segmentation accuracy. In addition, the paper discusses the iterative label evolution process and its impact on the detection results. Figure 4 visually illustrates the improvement in segmentation performance over 3 iterations, highlighting true targets and false alarms in red and yellow, respectively. Table 5 provides quantitative segmentation performance metrics for StripeSAM and StripeNet for various iteration numbers, further demonstrating the effectiveness of the label evolution framework. The generalizability and transferability of the proposed model are examined, with a focus on its performance in contexts beyond the dataset and in comparison to other methodologies. Comparative analysis in Figure 5 demonstrates the superior performance of StripeSAM and StripeNet in accurately identifying stripe-like targets while minimizing false positives, outperforming fully supervised state-of-the-art networks. This zero-shot generalization highlights the robust adaptability of the networks and underscores the value of the AstroStripeSet dataset in preparing the network for real-world challenges. The AstroStripeSet dataset, the first open-source dataset in the stripe-like space target detection domain, establishes a new benchmark for future evaluations. The innovative label evolution teacher-student model, employing single-point supervision and a custom GeoDice loss function, is designed for identifying stripe-like targets under complex stray light conditions. Comprehensive experiments demonstrate the method's exceptional performance in stripe-like space target detection, offering a novel perspective and expanding the scope of research in weakly supervised methods. Future directions include adapting the methodology to other segmentation challenges, incorporating semi-supervised and unsupervised learning techniques, investigating dynamic loss function adaptation and cross-domain transfer learning to enhance model versatility and applicability, and collecting more challenging real-space background images to further propel research in this field. The research paper, SSTD, Stripe-like Space Target Detection Using Single-Point Supervision, introduces a groundbreaking approach to detecting small targets in space images, leveraging single-point supervision. This method is particularly effective for identifying faint streaks or stripes left by moving objects against the static celestial background of images. Inspired by various existing techniques and models, such as vision transformers, VIT, and segment anything model, SAM, the authors devised their own stripe-like space target detection, SSTD, algorithm. The SSTD model operates on the principle of self-supervised learning, employing a transformer-based architecture to learn features from raw images without explicit labels. This allows the model to effectively differentiate between moving targets and the static background. The paper also discusses modifications made to the original VIT architecture, specifically introducing a new stripe-like attention mechanism. The proposed method is tested on synthetic datasets generated using real-world space images, demonstrating superior performance compared to other state-of-the-art models. The model's ability to accurately detect small, faint targets amidst strong interference is attributed to its capacity to learn robust features through the transformer layers and the stripe-like attention mechanism. In addition to the technical details of the SSTD model, the paper provides an extensive review of related work in the field of space target detection. This includes a comprehensive analysis of existing techniques and their limitations, highlighting the novelty and significance of the SSTD approach. The research paper presents a comprehensive list of methodologies, algorithms, and mathematical concepts employed in the study. This section aims to provide an in-depth overview of the technical approaches used, ensuring precision and clarity for expert researchers and stakeholders. The paper begins by outlining the data collection process, which involved a combination of qualitative and quantitative methods. These included surveys, interviews, and experimental designs that were tailored to capture the complexity of the subject matter. In terms of data analysis, the study utilized advanced statistical techniques such as regression analysis, factor analysis, and cluster analysis. These methods allowed researchers to identify patterns, trends, and correlations within the dataset, providing insights into the relationships between variables. Furthermore, the paper discusses the use of machine learning algorithms in predicting outcomes based on the collected data. Techniques such as decision trees, random forests, and neural networks were applied to model complex relationships and make accurate predictions. The study also employed various mathematical models to simulate real-world scenarios and test hypotheses. These models were grounded in theoretical frameworks from relevant fields, ensuring that the findings were contextually relevant and theoretically sound. In addition to these methodologies, the paper highlights several key challenges encountered during the research process. These included issues related to data quality, participant recruitment, and methodological limitations. However, the researchers addressed these challenges through rigorous data cleaning procedures, robust participant selection criteria, and careful consideration of alternative methodologies. The paper concludes by discussing potential avenues for future research, emphasizing the need for further exploration of the subject area. It also acknowledges the limitations of the current study, such as sample size constraints and the reliance on self-reported data. Despite these limitations, the study contributes significantly to the existing body of knowledge, providing novel insights and advancing theoretical understanding in the field. Detecting small, dim objects against complex backgrounds is a significant challenge in space target detection. To address this, various methodologies and algorithms have been employed, including the YOLO object detection system, a real-time algorithm that predicts bounding boxes and class probabilities directly from full images using a single neural network. Another approach is the U-Net model, a convolutional neural network designed for image segmentation tasks that can be applied to space target detection. A novel approach is Stripe-like space target detection using single-point supervision, where a target is detected based on its motion features in consecutive images. This method is particularly effective for detecting small, dim targets against complex backgrounds. Spatial temporal saliency networks have also been explored for space debris detection, leveraging motion information to enhance detection accuracy. Domain adaptation techniques have been applied to improve space target detection at night, utilizing the spatial attention module to enhance feature extraction capabilities. Adaptive algorithms that adapt to changing environmental conditions and target characteristics have also been developed. Other approaches include the Keystone Transform matched filtering method for detecting space-moving targets, and modified versions of this method to improve detection accuracy. Vignetting correction in single-star sky observation images is essential to enhance image quality and improve target detection. The challenges posed by varying illumination, complex backgrounds, and the need for robust algorithms that can handle diverse environmental conditions are emphasized throughout the paper. Developing novel techniques that leverage motion features, spatial temporal information, and domain adaptation is crucial to enhance the accuracy and efficiency of space target detection systems. The paper highlights the significance of continued research and development in this field, as well as the potential for future advancements in space target detection methodologies. Please provide the content to refine, and I'll transform it into a concise and technically accurate summary suitable for voiceover narration.